you here. Good morning, good afternoon, depending on which coast you are in. And welcome to our webinar, How to Improve Your 2D Drawings and Make Your Design Intent Crystal Clear. My name is Jen, and I'm actually on the marketing team here at Fictiv. I'll be helping to produce the webinar today, pretty much just making sure everything goes as smoothly as possible. I am speaking to you guys live from the balmy East Coast, Arlington, Virginia. It's about 92 degrees and 100% humidity, so really loving it over here today. So welcome, excited to kick us off. One housekeeping item and then one very exciting announcement for you all today. Let's get the housekeeping out of the way so then we can get to the fun stuff. We are welcome and open to any and all chats that you guys have today. Just make sure when you go to chat, you change your toggle to be chatting with both panelists and attendees. For some reason, Zoom webinar automatically defaults you to just chat with the panelists, but we want this to be a conversation with everyone that's joining us today. So remember to toggle and feel free to put that to panelists and attendees. Cool? So if you haven't done so already, you can go ahead and test it out, introduce yourself, let us know what you're hoping to learn today as we continue to get started. All right, now for the fun stuff. Super exciting announcement. In case you guys didn't see it in your email already, because I know you all read your email thoroughly, but every registrant for our webinar today will actually have early and exclusive access to a brand new platform feature offered through Fictiv. What is that feature, you say? It is automatically generated 2D drawings from your CAD upload. So everything that Kinsey is going to cover today in the weeds, how to make an awesome 2D drawing, you will have access for this to automatically happen for you on the Fictiv platform. It's awesome. I'm in marketing. I don't really know that much about engineering, and it's so cool. We're jacked up here about it at Fictiv, so hopefully you guys will be too. Later in the hour, after Kinsey is done coaching you guys how to create an excellent 2D drawing, she will actually be demoing this new feature on platform. So make sure you stick around for that, and everyone will gain access to that in Fictiv as early as tomorrow. So super exciting stuff. And in case you're brand new to Fictiv, don't even know who we are a digital manufacturing ecosystem. We help bring your parts to life, right? We are your destination for all things precision CNC, injection molding, you name it, specializing in tight tolerance, high quality parts that you can receive as fast as 2 days. Timing is everything, right, y'all? We need things like yesterday. We can help you make that happen. So, although we are a full service platform, Fictiv is really great at that human element. It's self-service, but we have human in the flesh eyeballs on everything that you do, helping you through every step of the way through DFM, order completion, you name it. So if you have a project coming down the pipeline, feel free to reach out. We'd love to work with you guys. Cool. All right, now I get to introduce my colleague, Kinsey Mead. Cheers. The crowd roars. Kinsey. Kinsey is a mechanical engineer with experience in product design and DFX for the consumer electronics industry. She's worked at companies including Microsoft and Apple, which is kind of a big deal. At Fictiv, she creates technical content to help other engineers up-level their understanding of key DFM and mechanical design principles. If you're not already convinced how much of a whiz kid she is, Kinsey has earned her bachelor's in mechanical engineering from UC Davis and her master's in mechanical engineering from Stanford University. And fun fact, Kinsey has actually moonlighted and done a little stint as a winemaker at a winery near Santa Barbara, California. So you can ask her all of your boxed wine questions until the cows come home. All right, so welcome everybody, and I'm gonna go ahead and turn it over to Kinsey.
Amazing. Thank you for that glowing introduction, Jen. I'm even more excited now to talk to you guys about 2D drawings. So we're going to start out with the importance of 2D drawings and why we still need them, even though everything is all about the CAD these days. Then we're going to move into the essential elements of a 2D drawings, everything you don't want to leave off, and go through a walkthrough of creating our own 2D drawing. We'll finish it up with some Q&A, but you can definitely type in your questions into the chat or the Q&A box in the meantime. So first of all, let's start off with a little poll. What do you think of when you hear create a 2D drawing? Is it your favorite part of your job? Or is it a little tedious sometimes? So let's see answers rolling in. Jen, do you have the responses?
I sure do. Let me end the poll and share the results.
Oh, awesome. Okay, cool. So hopefully everyone got to submit, but yeah, we have an overwhelming majority saying they're a little bit tedious. They are, a couple of people, maybe it's their least favorite thing. Some people said so useful. Yes, they are pretty useful and they are super important. So first, let's talk about why we need 2D drawings. So they communicate critical information about your part. You can see in this little video of the CAD, you can see so much from your 3D model. You can see all the features, get a sense for the scale and proportions of your part. Super useful, right? This is how we design parts and how we make sure things fit together. But just looking at this, do you know, without digging into annotations or other information, do you know exactly what material it is? Do you know what kind of finish you require? Do you know exactly what size tap you need for these holes? Not really. You can pull out the measuring tape within your CAD program and maybe measure some dimensions, but that's a little tricky. It's not a permanent solution. So that's the way we have 2D drawings. They have evolved over the years, before we even had CAD, to include all of the essential information, everything you need to make a part come to reality, right? These days we do have CAD, so you don't need to include every single dimension, but you still have all of these super important dimensions for the critical features, for the tapped holes, and the notes that you need to post-process and finish your part to get it perfect. It's also just a super convenient format. You can have it up on your screen, quickly refer to it, print it out, hang it up to display on the factory floor. You can easily carry it around and you can mark it up on the go if you're in a heated conversation with a fellow engineer trying to show your thoughts on design changes or maybe which points you need to inspect. Just very convenient to have around. And another super important point, manufacturers just still need them. A lot of manufacturers use it as an important part of their workflow to identify those important inspection points and the critical features and the tapped holes. Even if you have started utilizing model-based definition and making those annotations within your 3D model, not everyone has the software or the know-how to download and actually utilize those model-based annotations. So it's still super important to have a 2D drawing to communicate that critical information, help speed up the process, and make sure that you can meet those precision tolerances that will make your part, perfect. So let's get into the essential components of a 2D drawing. First of all, how do we even represent a 3D object on 2D, just on a piece of paper? How are you actually supposed to see what the part is going to look like? We have developed strategies for that. Again, 2D drawings have been around for a long time. So the main thing, one main part of a drawing is the isometric view. And this is kind of the 3D perspective view of your part. And we construct this by making the horizontal lines that are at 90 degrees from each other. Those are represented by lines that are 30 degrees off of the horizontal, as you can see here. And this is all going to be done for you in your 3D CAD model. I don't think people are really taking to the drafting table and drawing this by hand anymore, but it's nice to know why we do these things. And then to create these other views, like this top view, front view, and side view that you're probably familiar with, we use what are called orthographic projections. And so if you imagine your part within a cube or a box like this, the projection of each side of that box is going to give you those other important views. And so translating this to actually creating a drawing, you want to think critically about which views are going to be essential for your part. So if you have a pretty simple part, you can get away with just the isometric view and then maybe 2 other views to show, capture all of those critical dimensions. If you have a more complex part or a part that's not just shaped like a box, for instance, a triangle, as you may see later, you'll need a couple more views to show what the part will actually look like. You can also incorporate some extra views, like section views are super useful, super important for showing off internal features that you might not get a good sense for just from seeing the outside projections of that part. So you can see with a single part, it's good for seeing the depth of a drilled hole or this slot that's going all the way through the part. And then for assembly views, you can see as well, the section view is super useful to see these internal components. Otherwise, you might not have a sense for how wide they actually are. So section views are going to be a very good addition to your part if you have a lot of internal features. Detailed views are also very useful for seeing those small, complex areas that have a lot of details. So you can zoom in on that part and more easily dimension and annotate those views. Then once you have your views on your drawing, you want to add the dimensions. And so this is a tricky part that can take some practice, honestly, in getting a feel for what works and what looks good and what really communicates your intent. But you only want to include the necessary dimensions. And so these are hole callouts for drilled or tapped holes, as well as critical dimensions on features that maybe mate with another feature in an assembly. So features where you really need that precision tolerance to be met. And so when you choose these dimensions, you also want to make sure you're placing them on the views that make the most sense. So we can see here this 60 unit dimension, for instance, makes sense to place it on this view. You can see the entire face in this top view. If we were looking at the maybe right view of this part, it wouldn't make any sense to put that 60 unit dimension. You wouldn't, because you can't see that whole face. You also want to think about dimensioning from a common line or surface. So in this top view, again, we can see that we have chosen this reference or datum surface as the bottom surface. And so this is something to also put some thought into. Choosing your datum is important because this will matter for placing the part in the machine and fixturing it and then later inspecting it. So kind of what surface is mating with another part is a good way to think about this. But anyway, if we choose this surface 1, then we'll dimension from this surface to each next surface. So we can see from surface 1 to the next closest surface is a dimension of 8, and then to the one after that is 22, and to one after that is 30. And this works the same way if we had chosen the top surface as our new datum surface. We just dimension from that surface to each next closest surface. And so you may be wondering why we're doing it like this instead of maybe like this, where we have the width of that internal slot feature dimensioned. We do that so that the tolerances don't add up. As we can see, if we go back, having each dimension go from that common surface to the next closest surface is good because each of those dimensions will have a tolerance associated with it. And however, if we dimension each part separately and then we have to add them up in a tolerance stack analysis or something similar, then those tolerances will also add up and you end up with a greater possible variation and less precise parts overall. So in general, this is a best practice for dimensioning. You also end up with potential redundant dimensions if you dimension like this and then you try to add this overall 30 unit dimension. So you can see here, we've made that a reference dimension by adding parentheses. Oops, sorry. The presentation is getting away from me a little bit. Okay, so next, let's talk about other things you may see or use when you're dimensioning your part. aside from the dimensions, you also want to add these symbols to communicate your intention again. And so these are just some basic ones that you may see. Some are more common than others, but just to walk through them really quickly, we have the dimension origin symbol pointing to where the dimension starts from, and then counterbore symbols. So whenever you want to drill or mill a wider circle around a hole so that maybe a bolt will sit flush with the surface. Similarly, a countersink so that you can have a screw that sits flush with the surface. Depth will tell you how far down you want to drill or tap a hole. This all around symbol will tell you that a dimension applies all around a part. Between is the symbol that you'll see in those dimension lines, telling the reader that that is the dimension or length between 2 points. A target point can help you point out inspection points or other critical points. Conical taper and slope both will tell you the slope or shape of a part, and this is useful for measuring as well. And then square helps you point out that it's a square. We have even more symbols that we can use. So here are some basic GD&T symbols, and geometric dimensioning and tolerancing is a whole huge concept on itself. We could do an entire presentation on it, but I'm just going to touch on some of the basics that you might see on drawings here so that you can become a little bit familiar with them or refresh your memory, because I know there are a lot of these. But GD&T has 5 main categories of symbols or ways of dimensioning that we use, and those are the form, profile, orientation, location, and runout tolerances. So if we start with form, you have straightness, flatness, circularity, and cylindricity, and so this is controlling the form of your part. Profile, we have profile of a surface, profile of a line, and so these are controlling it'll give you a tolerance band that profile can be within. Orientation controls perpendicularity, angularity, or parallelism. Then we have runout, which this can be a tricky one, but circular runout or total runout is helpful. Like when you're inspecting a part, this means that you will rotate a part around its axis and then measure the variation in that part. And then location includes position, concentricity, and symmetry. So each of these symbols will also have a number associated with it that refers to the tolerance zone that symbol or the measurement can be within when you're measuring your part. And so again, lots of content here, could be a whole presentation, definitely something that's being used more and more commonly and something worth learning about. Some other symbols associated with drawings might be least material condition, most material condition, the tangent plane, projected tolerance zone, free state, diameter, that's a very common one, radius, not used quite as often, spherical radius and diameter, also not used as commonly, but you may find a use for them. And we also have controlled radius, statistical tolerance, the basic dimension. This means that this is the theoretical perfect dimension, and then there's always a tolerance associated with it though, because we can't really make perfect parts. We also have a reference dimension. As I touched on, this is just there for reference, but not used for actual measurement or to calculate the machining program. And then we have repeated feature symbol. And so this is useful if you have 5 of the exact same holes. You can say 5x diameter 3.00 or something like that. It looks like we have a question here. What if your groove width is the most important? So that can definitely occur. If that groove is being used to mate with another part, then you may want to find a way to datum, use that as a datum surface or feature, which is totally possible. And again, that gets a little more in the weeds with GD&T, but great question. Okay, so moving on to some of the other information that you'll want to include on your drawing, we have the title block. So this is going to include identification information around your part, like the name and number. And so your part name is usually a descriptive name, whereas the part number is how the part is identified on the BOM or in your CAD model. You can also add the engineer, drawing creator, manufacturer, or quality person. And this isn't, I haven't always seen this used consistently on every drawing, but it can be useful to show others who is working on this part, who you might want to notify if you make changes, and who else might be making changes to this part. You'll also see tolerances and notes on dimensions. So specifying the unit, specifying dimension or tolerances for dimensions where it might not be specified on the drawing itself. You can also identify the material and finish here, as well as the scale of the views that you're placing. You can also see the revision number and then applicable standards. So on this one, we have ISO 2768 medium, which again calls back to the dimensioning and tolerancing. Next, we have a revision block. And so in addition to having the revision number in the title block, you may want to have a revision block to show people the changes that have been made throughout the drawing's history. And so this can help others make sure they're using the correct drawing and the correct part to reference. And it can help identify also why the change was made or confirm that you have the correct information. Finally, we have the notes section. And so this is really important because it's all of the other information you could need to perfect your part that's not included in your title block or in the drawing itself. And so this could include more tolerance or GD&T notes. For instance, profile tolerances are sometimes stated in here, profile tolerance of 0.2 for all undimensioned surfaces. You might also have post-processing instructions like the surface finish that you need, any plating or coating that needs to be done, or any heat treatment. You can also have notes for testing and inspection, which parts, which dimensions you need to be inspected and how. And then you can have a note on identification, so engraving a part number or a barcode. All right, so let's move on to our own 2D drawing creation. We're going to use this fictive triangle part, just an example part that we like to use for various things. And so the first step is going to be creating a drawing, and your 3D CAD model software will usually have a drawing template that you can start out with, and your company or team might also have a template that they like to use with all of the information there. So the first step will be placing the isometric view, and this is just the default view that is in my CAD model as the isometric view. However, it's not my favorite view. We can't see all of the features, so I went back into the CAD and spun it around a little bit to create this view. You can see the curved surface on the other side. You can see more of the holes and just more of those features that give you a better idea of the intent of the part. So I'm going to place that view and also place my other projection views. And so starting with this view on the bottom left, which is kind of our front view. You can see here, again, just straight 2D view. And then if you rotate that 90 degrees, you get this side view. And so this is a good example of why we need multiple views. From this view alone, you can't really tell that it's supposed to be a triangular shaped part. So that's why we have multiple views. And then we rotate it 90 degrees again, and you can see all of the holes on the back. And so we can see some of these holes don't actually go all the way through because they're not visible on the front. So we'll see later when we dimension these that will show through. Then we also have this view at the top, again, rotating it 90 degrees around a different axis. So when we place these views, you want to think about the spacing and what makes sense in terms of not cluttering up the drawing too much. So you want to leave room for the dimensions that you'll need, as well as space for notes and a revision block. And so sometimes these go sometimes in the upper right and left-hand corners, but we're using that for some of these views. So we'll eventually put the notes down at the bottom here in line with the title block. One thing to keep in mind also when you're placing views is you do have some constraints. These bottom three views are always going to stay in alignment because to represent that this bottom face is the same face across all three views. And so you can move any one of these views side to side to increase the space between them. But if you move one of them up or down, the other two views will shift to accommodate. Similarly, these two views are always going to be aligned over that center line, again, to show how they're related to each other. So if you shift either one of these left or right, the other one will shift accordingly. Next, let's look at dimensions here. So starting with just some linear dimensions, you can control a lot. This is where your design intent comes into play, but you can communicate a lot with just how you dimension parts and how you add tolerances. So this first dimension on the left, 0.375 plus or minus 0.003, the dimension itself goes out all the way to 3 decimal points, and we have a tolerance associated with it. So that's a good indication that this is an important tolerance, important dimension. Maybe this is mating with another feature, and so it needs to be precise. On the other hand, this groove, the 0.13 width groove, is not quite as important, only 2 decimal points, and there's no tolerance associated with it. When there's no tolerance associated, as with this one, that's when we refer back to the title block where we have information about what tolerance to use when there's no tolerance identified. Here we have just the width of the part, and again, we can see this is going to be more of a precisely defined dimension. Next, we'll dimension some holes, and so we can see the same thing applies to holes. This dimension, again, has a tolerance associated with it, so maybe this is mating with a pin of another part or something. We also have a note on the depth, so this hole, as we saw earlier, is not going all the way through, but it's a blind hole that will only be drilled down to 0.5 inches in depth. Similarly, these two holes are not as precise. They also have a depth call out though, so more blind holes. Next, we are going to this hole with, again, no tolerances here. We do have a depth associated, and we also have the second line this time that's calling out a thread call out. So this hole is going to be tapped with a 1/4-20 UNC tap. And it's going to be tapped to depth of 0.63. And so this is an important call out whenever you're making drawings. Hole call outs and thread call outs are really important to identify for your manufacturer. A quick note, if you are on the Fictiv platform and the only thing you need to call out is a tapped hole, you can use our auto thread detection feature, which will detect threads, threaded holes that are identified in your CAD model. So that can be super handy, no drawing necessary. If you do need to call out other important dimensions or critical features or make other annotations, then you will need a drawing. And for that, we can auto-generate a drawing for you, which is super handy. Like Jen said, I'll show you that later. Then moving on to other dimensions. So this view has a lot of dimensions associated. Starting with some of these ones, you can also see with this 0.500 dimension, your tolerances don't have to be symmetric. So you have a different upper limit and lower limit. And that again comes into play if you're mating with another part, maybe there's an acceptable upper limit, but you don't want to go lower or something like that. Then we have another hole, another blind hole. And then this hole is going to be through all, so a through hole. And it also has a counterbore associated with it, which is going to be a little bit wider, but not quite as deep as the hole itself. Finally, we have our last holes on the other side, so another through hole. And then we have these 3 through holes, which are also tapped all the way through, as you can see from the note. And it's important to pay attention to the threading on these because we have another 1/4-20 tap, but then we also have an M6 by 1.0 and M4 by 0.7. So when you see that M6, for instance, that's going to be a metric tap, which means the M6 part alerts you to the diameter of the hole, and then 1.0 or 0.7 is going to be the length of a single thread. Conversely, with our inch tap, so 1/4-20, the 20 aspect means that there are 20 threads per inch. And so those are some good different things to know about taps, whether you're tapping in imperial units or in metric units. Next, we want to go down to our title block. And so, like I said, we want to identify the part with its part name here, as well as the size of the sheet we're using and the scale of these views. Then we have the title block with the creator of the drawing. And then we call out, this is a little small, sorry, but here we're calling out the units. So unless otherwise identified on the drawing, all units are in inches. So that's really good to know. All of these dimensions are in inches. And also good to know because we have a couple holes here where we did call out metric taps. So even though those are metric taps, we still want to know that the diameter itself that's called out is in inches because that is not called out any differently. Then we have notes on tolerances. So in this case, the tolerance depends on the size of the feature according to ISO 2768 medium, which is our standard that we're using here. Sometimes you will see that the tolerance depends on the number of decimal points in the dimension. So again, super important to pay attention to as you're dimensioning the drawing and if you're interpreting the drawing. Finally, we call out the material as aluminum 7075. And then for the finish, we say see notes. So next we'll fill out the notes section, which tells us some of the other post-processing information. And so first we're going to want to engrave the part number on our part, and then we want to media or bead blast all surfaces. We also call out a clear anodization type 2 finish. So all good post-processing information to have. Then finally, we add our revision block. And so maybe I created this drawing one day and then I went back and shifted a hole in zone 4B a little bit. So good to track those changes in the revision block. All right, that gets us to the end of our drawing walkthrough process. Just to reiterate that 2D drawings are important. They're still an essential part of the design and manufacturing process. And then so because it's so essential, you do want to make them really good. You also want to make sure you're only including those critical dimensions and callouts. The overall geometry will be controlled by the CAD file, which is for a CNC part going to be used to generate the CAM program for the CNC machine. But it's important to include those critical dimensions and hole callouts so that those parts can be controlled more closely and you can make sure they're more precise. Then you want to also make sure the notes are useful, including the necessary post-processing information for your part. And finally, overall, keep it simple. This will be easier on you and on the manufacturer to interpret and execute on the drawing. Cool. So next, I want to take us to a little demo. We're going to get to see what exactly this looks like on Fictiv's platform. So here I have, we're going to upload this Fictiv triangle part to the platform, which I've already done, and then we'll click configure. And this is where we say, okay, we want this to be CNC machined out of 7075 aluminum. And drawing, I don't have a drawing for this, pretend we didn't just create one. So I'll generate a new 2D drawing. And now we're generating. To save us some time, I will go to this drawing that I have already generated. And so you can see here, it places your views for you. You'll get an isometric view. You'll get at least 3 profile views, the top, front, and right. And then the platform will also give you any additional views that are necessary to show features that are not found in the top, front, and right views. You'll also get this tolerance block, which gives you the ISO 2768 medium tolerances. And it will also call out any thread specified at the time of the drawing generation. If you want to add more notes, however, and this is great if you're kind of early on in your design stage, you don't want to spend time creating your drawing. I know at least 64% of you said that it's a tedious part of your day. So if you don't want to do that, then you can create this drawing here, and then you can go and annotate it as well. So this is great if you want to add extra notes or make any other changes as you're going back and forth. But we can say things like, again, maybe I will add a little note here. There we go. We'll add a little note here saying we want to engrave part number. Maybe shrink that a little bit. Engrave part number. We still want to bead blast all surfaces. So that's great. Maybe we will also circle this, call it out as a critical dimension. So we're going to ask to inspect it. And whenever you have a note on your drawing that you want to inspect a part, then you'll be prompted by the Fictiv platform to add a certificate of add inspection to your quote, which is really handy. And so this is a great feature, great new feature that you now will have access to as early as tomorrow, as Jen said. Once you've finished annotating your drawing, you can save and close, and that saving and our software will see all of the notes that you've made, but you'll also know that a person is going to be looking at your drawing on the other side. Stop share. Apparently the screen share is funky, so we'll just stop sharing and I will answer your questions. Just find all of my chat. Yes, okay. So yeah, model-based definition, not quite ready to totally replace 2D drawings yet. Again, that's why we're here. Should drawings be made to most help the machinist make the part or most help quality inspect the part? Yeah, so that is a really good question because it can be conflicting, you know, more information for quality inspection. You might have a lot more callouts for the actual points that you want to measure, which can get in the way. So it's a tough thing to balance, but I would say it depends on your part and your function and your goals. So if your goals are to have a super high precision part and you're in the part of your development process where inspection and measuring is super important, and maybe you're doing more qualification and characterization of your process, maybe that's where you want to emphasize quality. So yeah, often though, people try to squeeze it all into one. Some good conversation in here though. Yeah, so let's see. This is a good question. Are you suggesting that hole size and thread profile are both called out? Also, does the machinist pick up the profile of the bottom of the blind hole from the step file, or should that be called out in the drawing? So drill tip or end mill. That's a really good question. I think if you do need one of those specifically, then you should call it out in the drawing, like specifically request, I want this hole to be made with an end mill. Otherwise, I think usually for like especially a tapped hole, I think it would be drilled and tapped usually, or drilled and formed. And then it is going to be called out from the step file, but for inspection purposes and you know, tool choice, it's important to call out in the drawing as well, so that they can see like the standard hole size and tap size that you need. Yes, so complicated parts, you will need SOPs in addition to drawings, separate drawings for quality. That is also a good tip. Oh, okay. Cool, and we're getting some Q&A as well. We have one. which is better, giving datum on the base of face or mention of profile tolerance and flatness and refer to that as a datum? So that's a good question. That gets really in the weeds of GD&T. You're always going to define your datum surfaces as first because that's where you're constraining a part and measuring from there. New feature request, use AI to predict design intent. Wouldn't that be nice? Incorporating GD&T into AI, I like it. We also have a question, can you do it the other way around and create a 3D model from a 2D drawing? So as far as I know, there are no softwares where you can input a 2D drawing and you'll get a 3D part. That would be kind of cool, but that's also basically kind of what you're doing when you're going into your CAD software. You know, you're referring to the design that you have, whether that's a sketch or if you created a 2D drawing first, although I think maybe that is a more outdated process. But yeah, you're going in, creating the parts yourself. That's CAD, that's designing a part. All right. We have a question, what is the Fictiv platform? So that's kind of, that's where I was demoing the drawing creation, but the platform is on our website. Once you sign up, you can upload your 3D model. It's free to sign up, super quick, but you can upload your 3D model and configure the part, then choose your, again, process, material, and then you can get a quote based on lead time that will be generated. You'll get automatic DFM feedback, and you can also generate your 2D drawing at that point. Yeah, so does Fictiv have an SOP for 2D drawings? In our help center, we have an article that will tell you what you need to have on your 2D drawings. Basically, if you don't need to call out critical dimensions, you can do it with just your 3D model. If you need to call out, again, only threaded holes, you can use the auto thread detection feature, which will detect threaded holes in your 3D model. Then if you want more than that, you can use the 2D generation feature that we just saw and annotate that to include information that you want to communicate. So, but yeah, it does depend on the manufacturer. However, the manufacturer partners we work with will use these drawings. So good question. All right. Cool. Jen, I think we've gotten to most of these questions.
Awesome.
So
great.
Back here.
Well, thank you, Kinsey. Thank you, everyone, for joining today. As a reminder, you will see the recording and the deck in your inbox tomorrow, as well as have access to that new 2D drawing generation feature from your upload. So you will have that available to you as early as tomorrow. So definitely feel free to check that out. If you don't want to do your 2D drawing by hand, you can use the Fictiv platform. So thank you, everyone. Looking forward to see you at future webinars, and feel free to reach out if you have any further questions. Bye-bye.